Okay. I will present today a Polish proposition for our spectrometer to send to not only Mars. At first it was called Martian Far Infrared ORE Spectrometer, but also for the moon and possibly other celestial bodies. And therefore the current name is Multiplanetary. So the acronym can stand, it's still MIRORES, but it's not only Martian. And this is important because Mars as an endeavor which is important for the next decade, I think, but this decade will be all about the moon. And therefore, in this talk, I will discuss both the celestial bodies, both Mars and Moon, in the context of ore deposits, in the context of metals. Metals are crucial for space exploration because they are, of course, source of metals per se, but the minerals that host metals host also oxygen, like oxides, for example, and also elements or isotopes that are important for energy, like helium-3 hosted by ilmenite. Metals can be used for construction, of course, also. And where to search for metals on the moon? I see university students smiling here because they saw most of those slides during the week, but there will be also a couple of new. So iron maps are excellent on the moon, and we have also excellent titanium maps on the moon. This come from the 90s, actually. This is a quite important mission in the moon exploration. It's called Clementine. That was NASA mission. And what they found is that both, this is iron again, and this is titanium, you can see they correlate. They are exactly at the same place. And these places are lunar mare basalt. So these gray areas, these lowland gray areas, maybe I can, is it visible in my mouse? Yes. So you can see them here. And actually we know from Apollo missions mostly that lunar basalts do contain a lot of ilmenite, which is a mineral that is composed of iron and titanium. So lunar mare basalts can contain from 2 to 20% ilmenite. So this is really a lot, much more than basalts on Earth. And also lunar regolith, if you wonder, it's quite abundant in ilmenite. So this is an example here. You can see some particles of yellow particles. This is just regular volcanic glass. But then you have also these dark particles that contain lots of ilmenite. And here in this lunar basalt, this is maybe not one which is rich in ilmenite, but you can see some dark spots which are ilmenites actually. So this contains maybe 2-3%, not this much more here. And we are even more lucky because there is a correlation between titanium and sulfur on the moon. So the correlation is not excellent, but good enough. And titanium is an element which is hosted actually only in the ilmenite, almost only in the ilmenite on the moon. And sulfur on the moon is hosted actually only by sulfides. And you can see if you analyze Martian meteorites, there is a lot of literature data, lunar meteorites. I will talk about Martian later, but lunar meteorites at first. You can see there are plenty of sulfides in the Martian meteorites, especially iron sulfides, but not only. There is also Pentland diethnickel sulfide. There are also copper sulfides. And now, the same as what we see in the Martian meteorites. We see that Martian meteorites host both oxides and sulfides, and they usually coexist. So like on the moon, we have situation that we have mineral assemblages composed of oxides. So these are these gray phases here, bright gray phases, and sulfides are yellow phases. You can see sometimes you have more sulfides like here and less oxides, titanomagnetite. This is PO is pyrrhotite, iron sulfide, and sometimes you have more oxide and less sulfides, but they usually occur together. And we know from Earth studies, so this is an ocean example from a mafic rock similar to basalts, and you can see also bright gray, these are oxides, this is ilmenite, this is titanomagnetite, and yellow are sulfides. So you have pyrrhotite here, here's a chalcopyrite copper sulfide. And what is beautiful, we know this from the Earth studies, that oxides contain plenty of siderophile elements and sulfides contain plenty of chalcophile elements. And those two together are essentially a half of periodic table, and a half which is quite important because many of these are really precious. For example, gold or also platinum group elements, but also silver and copper. And we know also from curiosity measurements that sulfides do occur on the surface of Mars. We have really robust data from X-ray diffraction. So this is mineralogical analysis of powdered samples, really precise. We not only know that we have sulfides, but we know which sulfides we have. We know we have pyrrhotite, which is iron sulfide, and we know we have pyrite, which is also iron sulfide, but with more sulfur. Okay, there are two sulfur atoms in the structure. In pyrrhotite, there's just one sulfur atom per one iron atom. And the sulfides co-occur with oxides, with hematite in red, or this is magnetite. But what is unfortunate, sulfides are very difficult to detect on Mars and on the moon. And this is because they have quite flat spectra in the near infrared range, which is available for our measurements. And also these spectra are quite similar to various pyroxenes, orthopyroxene, clinopyroxene. These are elements which actually make up half of Martian minerals. So these are really abundant, and sulfides, which are accessory, they are just dissolved in the signal then. But if you look for the far infrared spectrum, then sulfides present really fascinating spectral features. So this is amazing compared to the near infrared. So this is pyrite, the yellow one, the orange is chalcopyrite, the brown is marcasite, another iron sulfide, and these are laboratory analyses. If you check other methods, these are remote operated vehicles. I work a lot with ocean examples also, so I like this example. So these are hydrothermal vents from the oceans. You have excellent peaks of, or absorption peaks of pyrite and chalcopyrite. This is this gray range. So we are always in this 20 to 30 micron range. And also astronomers see those nice peaks of various iron sulfides in this range between 20 and 25 microns. But the best part is that sulfides have excellent spectral features in this range, but silicates, so these are these, and sulfates, those here, they do not have. So they will not interfere with our sulfides. So if we see anything here, then we are quite sure this will be sulfides. And we did even a simulation. So pyrite is actually the most common sulfide in the solar system, most likely. So we use this. We see that if we have at least 20% of pyrite, maybe even 10% in some cases, we can already see this in the orbit. So Shergotide is Martian meteorites. So this is a most typical rock on the Mars surface. This is just a basalt. And what is also good, interferences are scarce. So for the moon, you have no interferences with water. For Mars, there are some. Those are these red lines, but fortunately, they do not interfere a lot with the sulfide lines. So with the brown line for the marcasite, this is for pyrite, this is for chalcopyrite. They are quite clean from interferences. And you may wonder how it is that we didn't have far infrared spectrometer on Mars so far, and neither on the moon. And actually we had. This is a planetary Fourier spectrometer. This operates on Mars Express mission. The mission is already almost 20 years in operation. So this is an old technique, but actually it will be good, but the resolution here is 10 kilometers. So this is excellent to measure atmosphere of Mars, but not the surface, not geology of Mars, and especially not minerals like sulfides. So to show you this, I want to show you an example from another study, our planetary study in a planetary field analog. This is a picture of mine from March this year. You will not believe this is Andalusia because you have so many clouds. And it was even worse, it was raining all the week. But we managed to make a geological mapping, and these guys here are pyrites. So this is actually a block of pyrite, 80 kilograms. And this is not what we have everywhere on Earth. This is actually the best place on Earth we have for pyrite. And even with that, we, on a selected field, we've proven that you need at least to have at least, you cannot count on more than, on larger fields than 30 by 30 meters or maybe 30 by 60 meters that are composed of pyrites. So even I told you 20% would be enough. So even if we dilute this, let's say this is 30 by 30, even if we dilute this into 100 to 100 or 60 by 60, and okay, we can say we need a resolution of 60 meters, but PFS is 10 kilometers, so no chance to detect pyrite. That's why we proposed our instrument with a resolution of slightly better than 20 meters. So this should be capable to detect large deposits on the Martian or lunar surface. Not small, but large, yes. And this spectrometer is composed of two parts. One is optical part. This is a tubus with a primary mirror and secondary mirror, and an electronic part. And the optical part is a Cassegrain optical system. So it is composed of this primary mirror. The light gets reflected here first time, then second time on the secondary mirror. This is just a small sphere. And it goes to diffraction grating. And it has split into 6 different detectors to collect various wavelengths. So two are reference detectors, so we can measure 4 minerals at the same time. And each detector has a collimator in front of it. So these are 6 collimators. And we do tests on the drone. And on Earth, you may ask why we don't do this on satellite on Earth. We cannot due to the water interference. So even on altitude of 100 meters with quite a short column of atmosphere, we have quite heavy interferences. So we already lose 20% of signal on sulfides, okay? Transmittances are about 80%. For larger altitudes, we can forget. So we'll do our tests in this area. This is in Rudawie and Nowickie Mountains in Poland. These are so-called colorful lakes. This is actually a post-mining area, but it's really beautiful. Tourists love it. If you are in Lower Silesia, you can come. We have red lake, yellow lake, also green lake and blue lake. So this is probably the worst, the red lake. And there was intensive mining here. So this is an old shaft, and here you an old tunnel for mining. And these are these pyrite-bearing schists that we want to measure. We did geological mapping this winter, and we found that many of these rocks have significant pyrite content. So this, for example, 7%, but in weight percent, because pyrite is denser than other minerals, so in weight percent, this is 30. It's just an example. And in the first stage, finally, this will be ready to launch for Mars, but also for the Moon. I told you that we are interested with metals, of course, but also with additional elements like oxygen, which is in the structure of ilmenite, and also helium-3. And we know from the Apollo mission that there is excellent correlation between helium-3 abundance and titanium abundance, because ilmenite catches helium-3 from the solar wind into its crystallographic structure. So if we will be able to find ilmenite, we'll be able to find the best areas for helium-3. And actually for this mission, we have commercial cooperation with iSpace, but I truly hope this can be launched in more scientific collaboration within this mission, Polish mission to the moon that was recently announced by Polsa. And we'll see if we can hope this mission will be launched at the end of this decade, then I think it would be great to support it with our instrument. So thank you very much, and I welcome questions.
Thank you very much. Do you have any questions?
Could you repeat titanium what?
You showed some lunar maps.
Oh yeah. This one, right?
Yeah.
Mm-hmm.
So, when you want to do this, you some spectral analysis of reflected light.
Okay, so for titanium, this is an element, so we need short wavelengths to detect it. So that was detected already in 90s by the Clementine mission. This is X-ray, actually X-ray spectrometry. Then our spectrometer operates in far infrared, and this detects, bounds between. So this is infrared. So it sees bounds between sulfur and iron, for example. Therefore, we can detect minerals with this.
Thank you. I have also one question. To design such a sensor, there is a problem with optics and also dimensions. It's pretty big to have the good resolution. But you said 20 meters resolution. That means that in such a deep infrared, the length will be more than 1 meter, in my opinion. And that's it will create more problems and costs. Yeah? How you will deal with this?
Length In what? What length do you mean?
Length of the sensor.
Oh, okay. The length of the sensor is 30 centimeters. Only 30 centimeters, yes.
Okay.
No, actually 40. Sorry, 40.
40.
Yes, 40.
But the diameter.
And diameter is 30. So there is a scale here.
That we are designing also, but not such a sensor, but not so deep infrared, from 8 to 12, that we have much bigger dimension.
So, you know, this is a compromise between we can measure only one field at the time. There is no CCD camera, so we can measure only one field at the time. So this will be a field of 20 meters, but not divided into many fields.
Okay. The whole region which you observe in one shot of this device is only 20 meters.
Yes, 20 by 20 in 1 millisecond. And this is only we do not have a matrix of many pixels at the same time.
But we have that this work of our sensor is 20 kilometers.
Oh yeah,
with a resolution of 20 meters. That makes this dimension so big.
This makes difference. Yeah.
Okay. Thank you. Thank you very much. Oh, yes, a question, please.
Can you hear? Okay, sorry. What's the smallest body of ORE that you can detect, and the like how much pyroxene, not pyroxene, of your pyrite should there be at minimum, so you are able to detect it?
Okay. So if we have a surface of, let's say, 20 by 70 meters, this is roughly 350 square meters, right? So on this 350 square meters, we need 15-20% of it covered by pyrite.
Isn't that quite high for what we know about those rocks?
Sorry?
Like 15% of pyrite in this kind of large body, it's quite high, isn't it?
This is very high, that's true.
So
because
how many of those kind of bodies do you expect, and why would you expect to have, like more of those on Mars or Moon than?
I estimate you may have maybe 100 or 200 bodies of this size, maybe 1,000 or more in the entire
and how
Moon.
long would it take for your instrument to map entire Mars or Moon? Yeah.
So, during a mission of 3-4 years, we can probably find 2-3 such bodies.
Okay, thank you. We will switch to the next. Thank you very much.